Hey Google, I am so excited to be able to talk to you today about the methods that I use to conduct my research. Now, this is an engineering project, so I don't really have methods so much as I do have development. So I'm going to talk to you about how I developed the prototypes which I used to solve the problem that I identified in the last video. So I'll start with a brief review of that problem, go into the face tracking keyboard and the eye tracking mouse and how I developed that, and then I'll end with discussing the test setup and how I was going to make sure that the device worked as well as I wanted it to. So if you remember from the last video, the problem I'm trying to tackle is that quadriplegics are not able to use the mouse or keyboard and hence cannot use the computer to play computer games. So the first step was to identify a set of design constraints. So I got some from the game and from the user, and from there I was able to create a set of keyboard and mouse success criteria. And these success criteria are going to be common themes throughout my research, and I'm going to refer back to them so that way I can make sure that the device is performing up to the level that I wanted it to. So the first step of my research was to look at what are some solutions that exist on the market today. And because I realized that this problem is not a new issue, and I wanted to see what solutions exist in the market. And so I conducted a market survey. And what I found was that the devices on the market today advertised as helping to solve this issue are not adequate solutions. And the reason is because these devices, they have two fatal flaws. The one is that they cost a lot of money. These devices can cost well over $1,000, which is not affordable for this user demographic. Also, these devices don't have the usability necessary to play computer games. These devices are often just mouse emulators, which rely on an on-screen keyboard for keyboard input, and this is just not acceptable for gaming. So, in the year 2013-2014, I decided that I wanted to tackle this issue through the lens of wearable devices. So there I had several different design choices, and so I chose last year to prototype wearable devices, of which the most successful device tracked head movements and tongue movements to provide keyboard and mouse inputs. This device was highly reliable, and it was great and very performed at high accuracy. The only problem was that it relied on head and neck movements, which C1 quadriplegics cannot do, so this device wouldn't be usable for them. So this year I resolved to create a natural user interface which tracks facial gestures and eyeball movements, and this would solve the issues that the wearable device had. So I decided to use the Microsoft Kinect V2 sensor for the face tracking device. So let's get started on the face tracking portion of the development. So the Microsoft Kinect provides me with advanced vision processing algorithms which allow me to efficiently find a face in a given image. And these algorithms are paired up with a high-resolution camera and rangefinder, which allow me to efficiently find a face in an image. So I had fundamentally two choices. Either I use generic vision processing algorithms, which have existed for a very long time in the computer science world, or I use these new algorithms developed by Microsoft. So I chose to use the ones developed by Microsoft, and I equate it to being given an engine and asked to design a car. I was given the raw potential to do face tracking using these algorithms. However, I still had to actually do the face tracking and design an interface which would intelligently incorporate this potential and use it to the best of its ability. So let's talk about how exactly I did that. And so we'll start with the face tracking. So over here you can see the general flow of how the program finds a face, and then it uses that to interpret a keyboard command. So I had a couple of design choices to make when building my face tracking keyboard. I first had to choose which facial data do I want to collect, and so I chose to track the Candide 3 animation units. And you can see examples of the animation units here. These are actions that we might do every day, such as smiling or opening our mouth or blinking. And these animation units exhibit high reliability and are the data from these animation units I found are not very noisy, which makes them better for face tracking. So now for processing this data, I chose to use an artificial neural network, and it'll become more apparent later on when I talk about the neural network, why it was so essential. It mainly allows my device to be trainable for different users, and it allows for the device to recognize different variations of the same facial gesture, which is very important asset in using the device, because humans are innately not consistent in our actions. So for sending the keyboard commands to the game, I decided to use a PySketch to do that, and you can see the program flow off to the lower right hand corner. It starts with the user inputting into the main program interface, the main WPF. That WPF is going to send facial data that looks like this into the MATLAB neural network. The neural network is going to respond with what command it thinks the user is trying to send, the user intent. And then it's going to send the user intent through the WPF, and that's going to in turn ask the GlovePy PySketch to send a command into the computer game. So actually using the interface is a three-step process. The first is I call it the discover, train, and input phase. I had to actually especially construct this protocol to fit my interface, and this is going to ensure that the user is able to train the interface and make sure to recognize the best possible commands. So let's look at this a little bit more in detail. So the first step is there are 18 animation units. However, not all of these animation units can be done by every person. So the first step is to do some sort of rough elimination and see which animation units can the person actually accomplish. Because some of these are very difficult or very unique actions which some people cannot contort their face into. So the next step, that's sort of like a rough cut. And then the second step is to compare these animations, is to see how well is the Kinect sensing these animation units. So I'm comparing these yellow values here with the blue values directly above them, and that's going to tell me if the Kinect is seeing a difference in the command in the action when it's being executed versus when the person's just keeping a neutral face. So what these two steps together will do is give me a list of usable animation units. And from there, these are just sort of raw actions, and I can mix, match, and combine them to form inputs. For example, I have combined, there's a left half smile and a right half smile, and I can combine them together to create a just one that's called smiling. So I can mix and match these animation units, which are deemed acceptable and easily recognized by the Kinect, to create inputs for the interface. So these animation units are being interpreted by a neural network, and this neural network is going to allow me to recognize different variations of the same facial gesture, which is going to be very important to improve the usability of the device. One of the three criteria I determined was extremely important in building the interface. So this neural network is programmed in MATLAB, and it is a pattern. It's a classification neural network, and it is the neural network takes in the 18 animation units and it outputs the 9 different commands that the interface can execute. And it's got 3 layers, and there's 10 neurons in the hidden layer, and I had to do this really through an experimental process. Here you can see kind of how the interface is inputted into how the interface uses the neural network and how that's integrated into the rest of the code. So that was the face tracking. Now let's face tracking keyboard, and now let's transition into the eye tracking portion of the project. So eye tracking was a very interesting phenomena to work with. I had to actually construct 2 different control schemes for making this project, because you use the mouse differently depending on if it's a point of view game or a point to select game. So for point of view games, your character is panning around the scene. So I divide up the screen into 9 zones, and depending which zone the user is looking in, that's the direction that the mouse is going to move. For point to select games, the mouse is simply being set to wherever the user is looking. Now, the point to select games are more susceptible to these 2 types of errors up here. One of them is from the inaccuracies in the iTribe and the iTribe tracker itself, which is the device I use to do the eye tracking. And the other one is involuntary eye movements, and those are called saccades. So once again, with the eye tracking, it's the same situation where eye tracking is giving me, the eye tracking device is giving me the raw gaze data on the screen. It's telling me where the user is looking. It's giving me the potential to do eye tracking, but it's my job as the developer to create an application to actually use that potential. So now, if you look in the summary section and also in the method section, there is a video of me actually using the device to play the game Portal, which you can see screenshots of down here. And this game is pretty irrespective of the kinds of games that the user would like to play. So you can see that I actually am able to use the device to play the game Portal, and so I knew from that point that the device actually works, and I evaluated it qualitatively on that basis. However, I also needed to see how well it works, and I did that using a quantifiable technique. So the first step was to what I did was I looked at the keyboard and mouse in speed and accuracy. So in accuracy, for keyboard, I was looking at the ratio of correctly sensed commands to incorrectly sensed commands. And for keyboard speed, I wanted a more practical approach, so I had the user actually play the game Portal and through a couple of levels and saw how long it took to see if they can actually use the device to play a game relatively quickly. For mouse accuracy, I have this grid of randomly plotted points, and the user has to click these points in order, and that will tell me what is the resolution of the mouse device. And for mouse speed testing, I again wanted the practical approach. So I had a sphere, a 360-degree sphere, and the user is actually in this sphere, and they're looking at different targets to see, can they use the mouse to look around and pan around a scene, just like how they would in a game. So that concludes it for this section. We started off with a review on the problem, went into the development for face tracking and eye tracking, finished up with the test setup. In a future video, I'm going to go through the data and walk through how I interpreted that data to determine whether the device actually worked. So thank you very much. That is all. I will see you in the data section.